So the governing equation for jets was this, and then we had made our cell similarity analysis, and of course you have the continuity equation, and then we had made the similarity guess that it is equal to ax to the power p, or rather for u, not for u, for psi we had made eta, and eta was y over b x to the power q. Okay, this is what we were doing, and based on just simply by putting this inside our governing equation, we had derived that for self similar solution to exist, we have p plus q equals 1. Okay, and then we had shown that for a jet you have the momentum flux as constant. Basically this is equal to u naught square times h. So from here we had derived that, what did we derive? P equals 2q, something like this, q equals 2p. Okay, and so by combining these we saw that q is 2 by 3 and p is 1 by 3. Yeah, and then we were doing the similarity solution, so we had substituted these values of q and p here, and we had obtained the equation which was f triple prime plus ab by 3 nu f prime square plus f double prime equals 0. Okay, and then the boundary conditions for this were, so you have u of x comma y. What were the boundary conditions that we were using? U of x comma y is 0 for y tends to infinity. So this means, so when you calculate u from this psi expression, which is nothing but del psi by del y, that is 0 for y tends to infinity. So that would imply that your f prime equals 0. Okay, this was our boundary condition, the first boundary condition that we said, and then we said that eta equals 0, you have, or y equal to 0, you have v equal to 0 due to symmetric flow. Okay, and so from here we said that f eta equals 0 is also 0. Technically it has to be a constant, but since this is a stream function, we can put that arbitrary constant to 0, because the absolute value of stream function doesn't really matter in incompressible flows. Okay, the absolute value doesn't matter because you're anyways getting the velocities from derivatives of stream function. It's very similar to pressure, where the momentum equation is impacted by just the derivative of pressure, not the pressure itself. So the absolute value has no real meaning. You can shift it up or down by a constant value and the flow will not change. This was our first boundary condition, and then we had said that at f equal to 0 you have symmetry. Again, for y equal to 0 you have del u by del y as 0, again due to symmetry, and that implies, so u itself is del psi by del y, you have an f prime, and when you do a second derivative you get f double prime eta equals 0 equals 0. Okay, these were our boundary conditions, and as you will see soon that this is also something that will be required. Let's see if this is required or not, and we'll proceed with the algebra. So we have to solve this equation subject to these three boundary conditions. So the first step is recognizing that f prime square plus ff double prime is nothing but ff prime whole prime, right? So this is nothing but f triple prime plus ab by 3 nu, and then f prime whole prime equals 0. So that means this is some constant c1. Okay, and now if you look at ff prime, that is nothing but, so if you do take an f square, half of f square, you differentiate this, you will get ff prime. Okay, so this is f double prime plus ab by 6 nu f square prime c1. So we can again integrate this and write down that f prime plus ab by 6 nu f square equals c1 eta plus c2. Okay, now from here you see that for f prime, for f prime eta tends to infinity, for it to be 0, you realize that c1 has to be 0. So for f prime eta tends to infinity or even finite, c1 has to be 0. Okay, c1 cannot be some finite quantity. So that means we have to solve f prime plus ab by 6 nu equals some c2 times f square. So this is nothing but df by d eta equals some c2 minus, let's call this as capital K, k f square. You guys know how to integrate this. Okay, this equation can be integrated. What is the solution? What do you get when you integrate this? Hmm? What do you get when we integrate this? So we can write 1 by c2. You can either give it in terms of tan inverse or log. I think giving it in terms of log is easier. So we can take that f times square root k by c2 is some g. So df is dg times square root over k, and this is nothing but 1 by c2 square root c2 over k dg over 1 minus g square, which is 1 by square root k times c2, 1 by 1 minus g plus 1 by 1 plus g, right, and then a half dg, right. So this is 1 by 2 root k times c2 ln 1 by 1 ln 1 by 1 minus g plus ln 1 plus g, right, and then on the right hand side you simply have eta. So this implies ln 1 plus g over 1 minus g is 2 square root k c2 times eta. What do you get from here? Huh? What do you get from here? We can simply write as there has to be another constant of integration. Let's write it as c3. Okay, so this is, so let's write e to the power c3 as some k3 e to the power 2. Okay, this is what we get. So basically we have been able to solve this nonlinear equation. This is one of those cases where you can do that. Okay, not every case you can solve this nonlinear equation, and then you can substitute what was your g in terms of f and write down the solution. Okay. Any questions so far? Momentum flux. Yeah. Where were viscous losses? So this is not boundary layer, this is jet. Okay. Technically, there is no wall here. The viscous. So viscous losses is a very generic term. You know, there a lot of hand waviness can be done by saying viscous losses. What do you mean by losses? I'm not writing an energy equation. I'm writing a momentum flux term. Viscous losses usually mean loss of energy. Like if I imagine it to be because of the symmetricity, the middle line is not a wall. Is not a wall because there's no slip there. Middle line is not a wall. That is a problem in your intuition where you are thinking of this as a wall. Maybe you are imagining that wall is moving at a speed, some constant speed, but as you will see soon, this speed is not constant. This is not equal to u naught. It will actually decrease with x. Okay, so this is, if you really want to force an imagination where you want to think of it as a wall, then this is a wall that is stretching technically. Okay. Luckily, there are analytical solutions for a boundary layer over a stretching wall also, but maybe you can try to derive it yourself. So this is not exactly a boundary layer, but simply because of this these two conditions to be holding, we can use boundary layer theory, and they are not really holding. We did not obtain it from any physical principle. Notice that this delta and L, these are scales, so we can always choose a scale where these conditions will hold. Okay, these scales are like zooming in and zooming out at appropriate locations. So the only meaning of these two conditions together is that we are zooming in far away from the inlet of the jet, or if you want to think of it as an outlet, far away from this jet where it is emanating, and not so far away from the center line. Okay, if this height is h, usually in jets, in 2D planar jets, 50 h away from this point, you can see cell similarity experimentally, but you have to be 50 times that h. With the governing equation, the viscous term is not dropped, which is the case here. Then is there some intrinsic viscous losses? Like I know, but are there any viscous effects there? Yeah, of course, there are viscous effects. Viscous effects are there. There's no denying. Governing equation has viscosity in it. Viscous terms are not dropped. That's why. Notice this says momentum flux integrated from minus infinity to infinity. When you integrate this equation from minus infinity to infinity, the fact that far away you have hardly any fluxes, this term went to 0. Okay, it is very similar to, so you can derive a momentum integral for boundary layers as well. Okay, what you can do is you can integrate your governing equations over this line. Okay, so when you integrate this term over that line, what will you get? Del u by del y for y tends to infinity minus del u by del y here. But now here there is a wall, del u by del y is not 0 here. Okay, here we integrated from minus infinity to infinity. You could have integrated from 0 to infinity also, and symmetry dictates that del u by del y is 0, you would still get the same thing. I mean, the problem is symmetric, you will just get a half here because this is 0 to infinity, you will get a half here and you will get a half here as well. Okay, technically this equation, this form of equation is called a momentum integral. So in your intuition, you should not think of it like the momentum is constant. No, the momentum is definitely not constant. It's the integrated momentum that is constant, and it's not even integrated momentum. Technically, it is the momentum flux that is constant. It is the rate of transport of that momentum that is constant. Okay, it's very difficult to imagine this quantity, honestly speaking. Okay, you might as well imagine like half u square dy, so kinetic energy in x direction is constant, you might as well think of it like that. So it is minus infinity to infinity integrated quantity that is constant. You can derive a momentum integral equation for boundary layers as well. Okay, now if you look at this, f of eta equals 0 is 0, right? F of eta equals 0 is 0. So that means f prime of eta equals 0 is simply this constant C2. Okay. The reason why f prime eta equals 0 is important because that is the the x direction velocity. I mean, of course, there'll be an a x to the power p multiplying, but and b x to the power q dividing, but finding f prime eta equal to 0 is important. So finding the C2 is actually important. Okay. Now you can write down this solution. Okay. There are ways to convert this solution. So this is 1 plus g by 1 minus g. You take the exponential of this equation. Okay. So you get this equation, then you do a plus 1, you do a minus 1 trick, and then you will get that f is technically equal to square root of C2 over square root of C2 over k times tan hyperbolic square root of C2 times k eta. Okay, you will get this. When you substitute this g and f there, okay, you will get this, and then when you substitute that here, you substitute that f. So for u, you will have to compute f prime. So you'll have to differentiate tan hyperbolic. Once you do that, you substitute there, and then you can find basically this k. You can find k in terms of this u naught and h. Okay, you can look at Panton's textbook for this. I don't think that all the steps are there, but after here the steps are just algebra. I really don't want to, I mean, I have it in my notes, I really don't want to go into it. Okay, the eventual fact is that your solution is something like this. Okay, so the variation of the solution we have captured, there are some constants that we have to evaluate, which you can do at your own time. The variation of solution is important, it is tan hyperbolic, and then we have also found what is the eta. Okay, we have also found what is this eta, and your eta is varying as y over x to the power q was 2 by 3, right? Okay, and now from here what I really want to go into is, if you remember, we said that this quantity is not constant. Okay, this quantity is not constant, and I want to show you that this quantity is actually increasing in x. This is our mass flux and this is increasing in x. So u is basically del psi by del y. So a by b x to the power p minus q f prime of eta, that is your u. Okay, p minus q is what? P minus q is what? Hmm? Minus 1 by 3 f prime eta dy. I want to look at this term. Okay, so dy again I convert it into eta. Okay, I'll convert it into eta. So dy is nothing but b x to the power q, which is 2 by 3 times d eta. Okay, so this quantity is basically a. So b will cancel out, a times x to the power 1 by 3 minus infinity to infinity f prime eta d eta. So whatever your f prime is, you just differentiate this tan hyperbolic, you will get some secant square, secant hyperbolic square or something like that, and you substitute it here, you integrate it. eventually you will get a constant because this is a definite integral. I mean, this is improper but definite. Okay, you can evaluate those limits. So eventually you will conclude that your mass flux is increasing in x, and it is increasing as x to the power 1 by 3. Okay, and this brings us to the important point which we outlined before doing all of this derivation, that this quantity was not constant, it was equal to u naught times h minus something. Okay, so there is actually this minus of something will also be negative, and you can derive that it is a positive influx into the jet, and this fact that your mass flux is increasing in x, mass flux is increasing in x as you move further downstream, it is increasing in x. So there is more and more fluid that is being dragged by the jet. Okay, there is more and more fluid that is being dragged by the jet, so mass flux is increasing in x as x to the power 1 by 3. That's called entrainment. Basically it is happening far away from the jet. It what is happening is you have fluid that is coming in to the control volume. There is a mass flux from the side. That's why I was asking that the momentum integral, this entrainment flow will also have a contribution. No, because the thing is this is mass flux. In mass flux you have u dot n ds. Mass flux is u dot n ds. Momentum flux, first of all, momentum flux is a vector quantity. Okay, it has to be u times u dot n ds. So the x component of u times u dot n ds will be x velocity times u dot n ds. Even though u dot n ds is not 0, but x velocity here we are assuming it to be 0. There is technically very less x velocity far away from the jet, and that is why there is no momentum flux of this entrainment, but there is a mass flux of this entrainment. Okay, if you think about momentum flux, technically this is the x component of this quantity that I have written. Okay, x component of this will be u times u dot n ds, which is the momentum flux. The mass flux is simply this guy. This guy is 0 because this is 0. Overall, this is not 0. There we lose all of our assumptions of continuum and everything else. So how can you entrain more mass if you don't have mass? The jets in vacuum will be totally different. This is in here what we assumed is that we have a jet that is coming in, jet of a fluid that is coming in, and that same fluid is existing over in the atmosphere. So it is kind of like your submerged jet experiment that you guys have in your labs. You have a jet of air coming inside air. Okay, if you have a jet of air coming inside vacuum, then in fact even the pressure you cannot assume to be constant anymore. Okay, if you recall this equation here, we drop dp dx term. Why did we drop dp dx term? These are free jets. Jets, the atmospheric pressure is p and that is constant in x, and so once we reasoned that dp dy is 0, we said that dp dx is also 0. If your dp dx is not 0, then you have to account for that term in your jet equation also. Okay, so in vacuum we cannot expect all of this to hold. It's x velocity. We have posited that. And n direction is this. N direction is this, no? N d. So this is u dot n ds. So this is the mass entrainment. Mass entrainment will be this guy, no? And that's the term that appears here. If you recall, this was v dx integral. Okay, this was v dx integral. Any questions? Any? If it's not clear, you can still ask. Why is there a minus sign before entry? Of course, I mean the entrainment from that expression will come out to be negative, so it has to be positive. Of course, it has to be increasing in x. It's technically negative of entrainment. Okay, okay, because I have a so all of this algebra gave us a closed form solution, and it happens in practice. You can actually experimentally validate this solution also, but you have to be sufficiently far from the jet uh, outlet. So something like 50 h, 50 to 100 h if you are far away from the jet. So if you don't have an intuition, then so far away from the jet, you actually barely see a jet if your instruments are not very good enough. Okay, if your instruments are not very sensitive enough, you will barely see a jet, and that is the regime technically we are solving. Okay, very close to the jet, none of this holds. Okay, if you recall again your submerged jet experiment in the fluids lab, then you start with a with a position very close to the nozzle, you measure the velocity radially, and then you move downstream one by one. Okay, as you move further away downstream, you are actually improving the conditions of this approximation. Okay, you are making this regime hold better and better. So you can expect that. So technically in that jet, what you take the measurements up to 50 centimeter from the jet orifice, right? If you take it far away, let's say 1 meter, technically around 1 meter, 50 to 1 meter, 50 centimeter to 1 meter, you will see self similarity, although that will be a turbulent jet, so things are very different here. But if you can get a laminar jet, you will see self similarity. Okay, and these are basically very, you can think of them as academic solutions because they exemplify the power of self similarity and how to use your Navier-Stokes equations in approximations. And the approximation that we have been discussing is this. Any questions? No, not just that. REL is much greater than 1, and it's not a general comment that you can make. REL is much greater than 1. This is true also. So these assumptions give us this equation. This equation doesn't always have cell similar solutions. Okay, only under particular cases this equation has self similar solutions. And actually, if you look at your textbook, there is another case where this equation is valid. The equation is valid, but there is no self similar solution, and that is wake of a bluff body. So let us say you have a bluff body like a cylinder, okay, and you have uniform flow hitting the cylinder. Okay, now the wake, if you recall the boundary layer class and the flow visualization that we did, what we saw is that the flow separated, right? The flow separates from the cylinder, and if you look at the velocity profile in the wake, it will look something like this. Okay, and you can basically apply the boundary layer theory in the wakes as well. You can apply the boundary layer theory in the wakes as well. You can reach the same equation, but this won't have self similarity. You will not be able to find a condition where self similarity can hold. You have to do the algebra and find a contradiction. As I said, self similarity is one. Some indicator that we know that we can maybe approach. I haven't found it in my practice. Maybe there are more problems to look at. So far, whenever I've looked at self similarity in any of my research problems, usually you have to do the algebra and find a closed form solution to reach the conclusion, yeah, okay, self similarity holds, let's proceed with it. The other physical intuition of self similarity is that there are no external scales involved. Okay, and here what you can think is, in fact, in both of these cases, there is an external length scale that you are imposing. Okay, here what happens is you are saying you move far away from the jet. Now your intuition would say, okay, move far away from the body. Why don't you get a self similar solution? You will get a self similar solution, but that will be simply a diffusing solution. If you use this equation, you will get a self similar solution. Okay, so as it turns out, the non-linearity, if you are not that far away from the body, in which case here you might have found a self similarity solution, you won't find it here. It's just the maths doesn't figure out. Okay, technically this is the condition that will stop holding here, and you will see that there is a momentum flux. Of course, there will be a momentum flux, right? You guys have done this kind of a problem where you were given some flow profile there, and you were asked, okay, calculate the drag force on the body. Okay, I'm assuming in your introductory courses you have done this analysis. So once you have this kind of a control volume, what was the first thing that you noticed? Something very opposite to jets. What was it that you noticed? Instead of mass entrainment, there is a mass flux, there is a mass outflux here, right? Because if you have a rectangle, if you make a rectangle, then this will give you u infinity times whatever the height of this rectangle is. Here you will have some deficit from compared to u infinity. Where is that mass going? Mass is leaving the control volume. Okay, so this is sort of an opposite case here from here. This variable separation is also in the second solving it. If you use this equation, then yes, you will see variable separation can be used, but if you use this equation, then there is nothing you can do. You cannot you cannot proceed from this equation after that. You have to solve it numerically. If if I say what is the reason we are able to use self similarity, or what? Physically, I have no explanation to that. Physically, I have absolutely no explanation why self similarity works here physically. Mathematically, I can offer an explanation. Physically, I don't. I cannot. In any of the textbooks, I have never find any physical explanation of why jets not wakes. Um, none of my so far, none of my research has been able to answer that question. Why it works in one case, why it doesn't in another case. Physically, mathematically, it's all in front of you. And why is it called self similarity? Self similarity is because of, so basically what you're saying is that psi over a x to the power p, this function is a function of not y not x separately, it's a function of eta. So what it means is, if you have an x comma y point where you have, let's say, a value of eta, if you have another pair where you have the same value of eta, value of f there are similar to each other, or this quantity. Okay, so self similarity is very related to the concept of fractals actually. Okay, where fractals also, what you say is, if you zoom out enough, you're looking at the same solution technically. Okay, so you are maintaining something which is a combination of your two independent variables as constant. That is why you're getting the same function back. Okay, so the solution is not a function of two independent coordinates separately, it's a function of their function, and along that line where that function eta is constant, you will get the same value of f. Okay, so there are other cases of boundary layers also where you can use the boundary layer theory as we have described and find self similar solutions, or at least get the nonlinear equations and then integrate them, nonlinear ODEs. One interesting case is that of a 3D boundary layer. I am not going to discuss this in detail, I am just giving you an overview here. So, in 3D boundary layers what you have is, so far what we have been looking at is a flow like this. Okay. Okay. In 3D boundary layers what you do is you add a component which is span wise as well. You add a span wise component as well. Okay. So, if you looked at the streamlines they will probably be going something like this. Okay. If you looked at the steady flow streamline, they'll be going something like this. Why are 3D boundary layers important? Because if you look at the fuselage of the airplanes, you have, let's say you're looking at the top view, you have this as the fuselage and this is where the wings start. Okay, this is where the wings start. Now what happens is, on the body of the airplane, on the fuselage, you have a boundary layer that is forming, which is causing a span wise flow on the wing, and there is obviously a flow that is hitting the wing as well. So, the superposition of these gives you a span wise flow as well as a downstream flow of the wing on the wings, and essentially in your on your wings you do not have 2D boundary layers, you have 3D boundary layers due to the span wise flow caused by the fuselage. It is not just a wing that is flowing, the whole body of the airplane that is floating. Okay. So, that causes so if you imagine this as the airplane and this as a wing, as the plane moves in this direction you have a boundary layer that is forming and that is resulting in a flow outward. Okay. And that is giving you the 3D flow on the wing, 3D boundary layers on the wing. In these cases also you can formulate the self similar the boundary layer equations, you can formulate the self similar equations, you cannot solve them. Just like you were able to solve here in jets, this was very peculiar, you cannot solve it in this case, the boundary layers. There are other cases also, and those are of, let us say, axisymmetric boundary conditions, axisymmetric flows, sorry, not boundary conditions. Okay. In axisymmetric flows what you have is, you have, let us say this as z, you have r that is a function of z. Okay. This is the body of revolution. So, this is the axis and you have revolved something like a cone, you can imagine a torpedo or a missile or something, and then you have boundary layer on top of this. Here also you can formulate the self similar equations, a self similar solution. You cannot solve it analytically, you can at least get something of an equivalent of the Blasius boundary layers. Okay. Another case where this is useful is that of a mixing layer. So, mixing layer is something like this. So, just like so far in all our cases upstream, far upstream we have been imagining a uniform flow. A mixing layer is something like this. Okay, you have a u1, you have a u2. Okay, you have two different velocities that are coming out. Okay, this is the plane that is separating them, and what you see downstream that is happening is, of course there is a deficit of momentum, there is a difference in momentum. So, you can imagine there will be a huge viscous stress on this. Okay, and as you let it flow downstream, the viscous stress will result in some diffusion of this jump of velocities. Okay. So, you basically u2 will try to diffuse into u1, you will try to diffuse into u2. You can think of it like concentrations as well. The governing equations are non-linear. In concentration cases you will get a linear governing equation. So, these will try to diffuse into each other. Okay. So, you can formulate these layers and you can formulate the analytical solution of the self similar equations here. The bidirection bidirection forces. You were saying the fluid itself of the water boundary might move. There is no boundary, there is no plate, this is not a plate. Yeah, fluid won't move, fluid doesn't move, the velocity stress, it is the shear stress, the force is in x direction, it is not in y direction, it is a shear force, it is mu del u by del y. So, it will try to slow the flow down, okay, it won't move up. Mixing layers are important. If you look at your supersonic thrusters of a lot of jet planes, you will see what is happening there is there is, let us say, a supersonic thrust here, but these thrusters are not alone. Okay, there is a flow that is coming from the annulus, outer annulus of these thrusters as well, and that flow is usually not supersonic. Okay, that flow is because of some bypass that was done in your jet engine. So bypass is basically not all of the air is used to do the combustion in the combustion chamber and spin the turbine. Some is used for cooling and all of those things. That bypassed air that is flowing, that will be flowing from the outer annulus. So you will form a mixing layer type of a situation here. You can think of jets as very extreme cases of mixing layer where one of that U2 is 0. Jets can be thought of as extreme cases of mixing layer where U2 is 0. You could, in that case, you could travel, you could translate with one of the velocities U1 or U2 and you will get a jet case. Okay, so you can imagine that solution of mixing layers will be very similar to jet solution. Physically, you can think about jet as a combination of two mixing layers basically. Okay, so mixing layer is something that is even more fundamental than jet. Now, before closing this discussion, I wanted to give you some basic. So, what is the practical use of boundary layer? Okay, boundary layer theory. We started formulating this because we were not satisfied by our high Reynolds number flow equation, which gave us the inviscid equation, and then inviscid equation said that, oh, there is no drag. Okay, if you remember our flow past a wavy wall, the inviscid flow past a wavy wall, if you go back to the solution, we said that, oh, there is no drag on this wavy wall. Even on a flat plate, when you have just a plate and you have a flow u infinity, if you just look at the inviscid solution, you don't get a drag, but we know there is a drag force that is exerted on this plate. So practical use of all of this is eventually to calculate what is known as the skin friction drag. And technically this skin friction drag, so if you look at your flat plate boundary layer, the skin friction drag is due to the shear stress here, the del u by del y at y equal to 0, technically mu del u by del y, and this quantity is called your shear stress at the wall, usually written as tau w, and it is mu del u by del y at y equal to 0. Okay, now if you go and look at your our zero pressure gradients boundary layer solution, then we said that this u is some u infinity f of eta, where this eta was, so if you remember this, all of this we did in dimensionless quantities. If you do it in dimensional quantities, then we have y by delta, and then we have square root of x by L. We had something like this for eta. If you go back, we had y by square root cx and we took c as arbitrarily 1. So this is what we have. This is basically y over square root x square root L over delta. Remember that we were looking in the regime when delta over L is 1 by square root REL, and so delta is equal to what is square root REL. So this is L by square root of u infinity L over nu. So delta over square root L actually is square root of nu over u infinity. So this quantity is actually y square root of u infinity x, no, u infinity over nu x. Okay, so this means what is del u by del y? Del u by del y is what? If you look at this, del u by del y is u infinity f prime times square root of u infinity by nu x. Okay. So, if you substitute this in tau w expression, then tau w is mu times del u by del y at y equal to 0. So, u infinity to the power 3 by 2 by square root of nu x f prime at y equal to 0. What is eta? Eta is 0. Okay. And now from here what you see is this mu is rho times nu, and then one nu cancels out. So, you have a square root of nu u infinity to the power 3 by 2 by square root of x f prime 0. I can multiply divide by square root of u infinity, and what I will get is u infinity square and this means this tau w over rho u infinity square is f prime 0 over square root of this quantity is nothing but Rex. Okay. And this quantity tau w by rho u infinity square, technically with a half, is called the skin friction coefficient. It's a dimensionless quantity. Okay. On top also you have units of stress, and bottom also you have units of stress. It's a dimensionless quantity. It's very similar to your drag coefficient or whatever coefficient you want to formulate. Force over rho u infinity square times area. There is no area, we are working with stresses, so it is force per unit area divided by the some dynamic component of stress that you can formulate to non-dimensionalize. And so what you see from here is that if I want to know the stress at any location, I just need to know this f prime 0. Technically, to solve your boundary layers stress due to boundary layers, this f prime 0 is all that you need. Okay, so if you can solve the Blasius equation and evaluate this f prime at y equal to 0, you are done, or eta equals 0 technically. You so notice that this is still a function of x. So, if you want to calculate force per unit depth, let us say you have a plate of length capital L, you want to calculate force per unit depth, then you will have to do u infinity rho u infinity square f prime 0 square root of nu by u infinity x dx from 0 to L, and this will be your force per unit depth on a flat plate of length L, capital L. Okay, so this is the most practical thing that you could obtain from your fluid dynamic analysis. Basically, if I have a plate like this and I have flow that is coming in, imagine this dimension is almost 0. I have a flow that is coming in and grazing past this. What is the force on this guy? Any questions so far? Any questions? all of this that we have discussed technically is not an advanced version of boundary layer theory. Okay, we can have a full course on boundary layer theories and looking at different boundary layers and where they are applicable. Okay, this is you can think of it as an introduction to boundary layer theory. After knowing this, you should be in a situation of where you can better understand any of your simulations or your experiments that you are doing as part of your projects which involve boundary layer, if they involve boundary layers. If they involve flow past any body, or you have a wind tunnel also that you are using, then you will have the effect of boundary layers which will be which will have to be accounted for somewhere. Okay, any of your projects, any of your other uh, type of non-academic internship projects in core areas where you need flow past a body, boundary layer is something very basic. Okay, now so far in our course what we have been looking at, so what we have been saying over and over again is that Navier-Stokes equations are nonlinear equations. Okay, and what you will see is we have not been looking at all the possible solutions of these equations. Even in case of jet, for example, we solved a solution. Nonlinear equations, as we know from our experience in algebraic equations, have multiple solutions. They don't have just one solution. They may have multiple, they may not have multiple. We have to prove that what are the other solutions and if they exist or not. Okay, for example, you have an equation for a pendulum. Let us say a very simple pendulum. This is L, this is M. You have it in gravity. So what is the equation of this guy? Let's say this is theta. What is the equation? So you have ml square theta double dot equals minus of mgl sin theta. Okay, so theta double dot equals minus g by L sin theta. Is this a linear equation or non-linear equation? Non-linear. Why? Because of sin theta. Okay, if we did an expansion for very small thetas, we will get theta minus theta cube by 3 and so on and so forth, and there are non-linear terms there. How many solutions do you know? How many static solutions? So when I say solutions, I mean how many static solutions do you know of this equation? Steady solutions. How many steady solutions do you know of this equation? How many steady solutions are possible for this equation? If you have a pendulum, how many steady solutions do we have? Hmm? What are the values of theta where you have steady solutions of a pendulum? Steady solution, just think about steady solution, nothing else, don't overthink. Where sin theta is 0, that's where you have steady solutions, right? Where is that? Theta equals 0 and theta equals pi. Okay, these are the two steady solutions of your pendulum, of a simple pendulum. Theta equals pi and theta equals 0 are the two steady solutions of your pendulum. But in reality, I don't think you ever experienced this. I mean, you can force by accelerating this point here, but if you just leave the hinge point like this, you never experience this solution, you always experience this solution. Why is that case? Why is that? Why do you never experience this, but you always experience this? Even in case of this pen, the moment I let go of it strongly, I simply get something like a solution that you see. It's related to stability of one solution. This guy, this steady solution that you found is actually unstable, and this steady solution that you found is actually stable. And very similarly, what we can say is the Navier-Stokes equations that we have been looking at, and especially these boundary layers, jets and everything, we have been solving steady solutions. How do we know in practice we are going to experience these? How do we know in practice? We found a steady solution of a nonlinear equation. That doesn't mean it is the solution. It might as well be an unstable or unstable solution, and some other solution might be visible in your actual boundary layers. Okay, and this some other solution okay, is actually the turbulent flow. It's of the same governing equations. It is not a steady solution in the very strict sense, but in the mean sense it is a steady solution. The turbulent flows are steady mean wise, not fluctuation wise. We'll have more discussions on that as we move to turbulence, but the fact that you have a solution of your nonlinear equations, a steady solution of the nonlinear equations, doesn't mean you will always observe it. It is also very important to look at the stability of that solution that we have found, okay, and that brings us to the concept of dynamic stability. We will look at dynamic stability of generalized dynamical systems. The reason why I am saying dynamic stability is because this is different from buckling. Buckling is also an instability. If you are pressing a rod or a pipe or something and you force it, you will see the cross section. If it is a pipe, it will collapse. If it is a rod, then it will bend. That is also stability, but that is not dynamic stability, that is static stability or instability. We are looking at dynamic stability or instability. We are looking at fluid dynamic stability or instability, to be exact, or as often it is called, hydrodynamic stability. Okay, we are going to look at it from the perspective of a general dynamical system, not a very general dynamical system, but what is required from our for our analysis. We are going to look at this, and so for example, you have a system of, or you have a degrees of freedom, some degrees of freedom of your system. Let us say you have n degrees of freedom of a system. Then a general dynamical system, you will write, let us say this is your y tuple or a y vector. You will say this dy over dt is f of y comma t. Okay, this is, let us say these are some degrees of freedom of a system, and this is its dynamical equation. Okay, this could be anything. For a pendulum, you have a single you have a single second order equation. You can convert it into two first order equations. Okay, you can write d theta by dt as omega, and then you can write d omega by dt is minus g by l sine theta. You can write it as a system of first order ODEs. If you have higher order ODEs in your system, you can convert, if you have nth order ODE, you can convert it into a system of first order n ODEs. Okay, so in general you can always write a dynamical system like this with finite number of degrees of freedom. This word finite for this particular case is important because in fluids we have an infinite degrees of freedom, because we have a PDE, we don't have an ODE. Okay, so things will be a little different, but I will introduce using dynamical equations. I will introduce dynamics stability, and then we'll apply it to fluid dynamic analysis.